Hi guys, welcome to the next lecture of our series. So today we will be talking about domain of any particular function. To understand that better, let's first recall the definition of a function, say f. For each x belonging to the domain, we say there is a unique y which belongs to the codomain such that fx is equal to y. What is this scenario like? So suppose this is a set A and this is a set B. We are relating the elements in the set A to the elements in the set B. And this relation, we want it to be a function. If we want it to be a function, in the previous lecture, I explained to you what is a function and what is not a function. So we understand that your inputs will lie here. Some x's, we may call them, and the output will lie here. Output would be of the form y equal to fx, right? For any particular relation to be a function, every input in A must have an image in B. For each x belonging to the domain D, here I've just given it a name A, there should be a unique image. Let's not talk about the unique image part right now, but let's talk about the part that for each x belonging to the domain. So the crux of the story here is that we call the input set, the valid input set, domain for any particular function. Let's take a very general example. Suppose I want to prepare a glass of cold coffee for myself. What would I require? I would require certain ingredients. I would require coffee. I would require sugar. And I would require some sort of milk or milk substitute to prepare a glass of cold coffee for myself. These are the ingredients. And once they are mixed and, churned up, it gives me my cold coffee. This is the output that I will get. So these three ingredients that you see, they're a part of the domain. They form the domain for the preparation of a glass of cold coffee. So that's the essence of that's what domain for any function means. It means a set of ingredients. It means a set of all inputs. The possible value of x that you can plug in order to get a valid value of y, that is your output. Domain is the set of values allowed to plug into our function. That's the whole idea of domain. Let's take another example. Suppose we're talking about an assembly line to manufacture televisions. So there are a lot of chips required in order to create the screen and create a functional television, right? So all the electronic instruments, all the chips required, everything that goes into creating a television is the input or domain for that function. What is the function there? Creating a unique television that comes out. Like as I said in the previous video, function works like a machine. This time I'm taking this machine to produce televisions. So all different parts required to produce one television is your set of inputs, and the output that you will get is a unique television, one individual television. Okay? That's the whole idea of domain for any given function. Else, if we say that f is a function from a set A to B, the picture would be something of this sort. And what domain means is that whatever is here in A needs to have an image, needs to have a unique image, but the uniqueness part is something that I'll talk in range. Right now for you, just one part of the definition for a function, which is that every x in A needs to have an image. Hence, all these x's are also called pre-images. So in this sense, What is domain? Domain is the set of all possible pre-images, which basically means that these entries will definitely have an image. It's the set of input. It's the set of all pre-images, set of all x's for which the function is defined. It is plausible to put them as an input. Now, why I'm talking about it? The reason why I'm talking about it is that generally when you're asked questions and you're provided with, okay, assume that f is a function from a to b, your question should be that a is already given to me. Then why is a particular question asking me to find domain for this function? Many questions will ask you that. Many exams, many questions will be asked to you that find the domain of this function f. And if a is already provided to me, your question would be to yourself, why am I even bothered about this question? Why are they asking us to find the domain? There is a reason. Because there are scenarios where you can have some sort of restriction towards the input. Let's start with a very simple example. Suppose y is equal to 1 upon x. And the question is asking you, what is the domain for this function? So you quickly have to think, what all numbers x can I put into this function so that I get a valid output out of it? Well, if I put 1, I will get f1, which is simply 1. If I put 2 as an input, I will get 1 upon 2, which is a unique number that you are getting out. What if you put x equals to 0? What's going to happen then? Your function will look like 1 upon 0, which is a number not defined. There lies a problem, and there comes the question of figuring out domain for any given function. This is not a valid number. So here you cannot plug in 0. 0. 0 is a problem here. Hence, I will take all other x's except for 0. In terms of mathematical notation, I will take all real numbers denoted by this symbol r except for 0. So I'm going to delete 0 out of the set of real numbers, and I will call that as the domain for this particular function. So whenever you put an input, an output must come out. Otherwise, there lies some problem in the domain. To emphasize on this point, let me take up another question. With you guys. Suppose now the function is 1 upon x minus 1, and I want you to find out the domain for this function. What happened in the previous example? Why was 0 not a plausible entry for an input? The reason was that the denominator was getting 0. When the denominator in a fractional form, in a rational form, denominator becomes 0, then the number is not defined. That was the problem. So our domain would be any number which is not making my denominator 0. Denominator should not be equal to 0. That's the case. And because of that, what will happen? I will say that x minus 1 should not be equal to 0, which implies that x should not be equal to 1. All other real numbers, even 0 is fine this time. But this time, 1 should not be a part of my input set because I cannot take 1 as an input. It will not give me a valid output. That's the problem. It's very essential for us to also understand how we can write the domain, in what ways a domain would be written, and you should be able to recognize those notations. There are two ways how we can write down domain for any given function. One is the interval notation. The second is the set notation. Now let's understand what these notations are like. I'm going to take you back to the previous question. So we figured out if fx is equal to 1 upon x, and only real numbers we are considering as inputs, then we know that x should not be equal to 0, or in other words, r minus 0 is the domain. If I have to represent it in terms of interval, how you can create your interval on the number line? Let's see. First, let's see it on the number line, and then we'll write it down. So on the number line, 0 is here. All the real numbers to the left of 0 are fine. So an open interval notation here, an open interval notation on the right also, because everything on the right is also plausible input. Everything on the left and everything on the right. So which means that we can write down in terms of intervals, we can write down entire real line minus 0 in terms of an interval could be written as minus infinity to 0, open interval, that means 0 is not included, union with open 0 to infinity, that means again 0 is not included. What this interval notation is giving you is that either your x's should be to the left of 0 or they should be to the right of 0. They're fine inputs. We are okay with them. We will get a valid output with them, but with 0 we will not. So this interval notation excludes 0. So that's the first way. And the second way is to write it down as a set notation, which would mean that you're constructing a set. If I call domain set D, the set notation is curly brackets, right? So it's the set of all x's. What kind of x's are these? Everything except for 0. So it's a set of all x's from R such that or subject to x is not equal to 0. Simple. This is the set notation. You can write down your domain in either of these two ways. Can you think of some more functions where this kind of a problem could arise? Which kind of a problem? That we have some sort of restriction on the input? Let me give you a question. Suppose the function provided to you is square root of 1 upon x minus 1. What's happening here? You have a square root function, even root. When you have an even root function, the input that you put in here has to be greater than or equal to 0. For every even root function, input should be strictly greater than or equal to 0. If that is the situation, then with our input is 1 upon x minus 1, then that should be greater than or equal to 0. When is this possible? Now, this is a numerator upon denominator form. And we want numerator upon denominator should be greater than or equal to 0. Now, your numerator is 1, which definitely is strictly greater than 0. So, which means the only case possible is that my denominator should also be greater than or equal to 0. Then only I'll have a positive entry, 1 upon x minus 1. So this would imply that x minus 1 should be greater than or equal to 0, which would imply in turn that x should be greater than or equal to 1. When x would be greater than or equal to 1, what will you have? You will have 1 upon a positive number, which will give you the fraction as positive. The problem here is that we have taken greater than or equal to, yes, even root input has to be greater than or equal to, but what the problem here is that denominator cannot be equal to 0. So here, instead of denominator greater than or equal to 0, the denominator should be strictly greater than 0. You cannot take denominator to be equal to 0. Hence, from here, what you will get that x should be actually, including this, x should be strictly greater than 1. In terms of notation, interval notation wise, the domain D is essentially open 1 to infinity, everything is okay. In terms of a set, we can say that it's a set of all x's such that x is strictly greater than 1. And we have our answer. Let's understand this process using another example. This time, a little difficult one. So what do we require here? We require to find out the domain for a function square root of minus 1 upon x plus 1. What do we have here? Minus 1 upon x plus 1. In the previous example, you understood that the input for a square root function, even root function, cannot be negative. So whatever is inside this square root has to be greater than or equal to 0. That's the condition for domain, right? Now I'm going to take the LCM here. So it's going to be -1 plus x whole thing upon x should be greater than or equal to 0, right? Now again we have a numerator upon denominator form. For it to be greater than or equal to 0, suppose the concerned numerator is 2 and the concerned denominator is 3. Clearly, this ratio is 2/3, which is greater than 0. Suppose now I take the numbers as -2, your numerator, and -3 as your denominator. The numbers are negative, but the ratio again is 2/3, which is greater than 0. So what is it telling you? A numerator upon denominator form could be positive under two scenarios. Either both the numbers, numerator and denominator, they're positive, or both are negative. Either numerator greater than or equal to 0, and simultaneously denominator should be strictly greater than 0. In the previous example we saw, we cannot have 0 as the denominator, right? Or else both are negative. Numerator is less than or equal to 0 and denominator is strictly less than 0. Let's start with the first case, that both are positive. So that means -1 plus x is greater than or equal to 0, and simultaneously x is strictly greater than 0. Now -1 plus x greater than or equal to 0 would mean that x is greater than or equal to 1. And x also needs to be strictly greater than 0. Now you have to think of the numbers which would be greater than or equal to 1 and would also be strictly greater than 0. What are those numbers? Well, if the numbers are greater than or equal to 1, they're automatically greater than 0. Hence, from here, what do we get? We get that x should be greater than or equal to 1. If that will happen, then numerator upon denominator will automatically be positive. That is greater than or equal to 0. Now the other side, that is when both are negative. So -1 plus x is less than or equal to 0, and simultaneously x is less than 0. This would mean that x is less than or equal to 1 and x is less than 0. Now you have to think of numbers which would be strictly less than 0, as well as it would be less than or equal to 1. What are these numbers which will be lesser than 0 and also lesser than 1? All the numbers which are lesser than 0 would automatically be lesser than 1. So hence from here, what do I get? I get that x should be less than 0, strictly less than 0, because we cannot take 0 in the denominator. Now what is happening is either x should be greater than or equal to 0. So what is happening here is that either the input x should be greater than or equal to 1, or it could be strictly less than 0. In both the scenarios, the input, the entire input that we have, -1 plus x whole thing upon x, that would turn out to be positive ratio. Now, either or in set theoretical manner would give you union, could be denoted as union. In terms of interval, let's see what we can write it as. So I'm going to first write it in the interval notation, number 1, interval notation. Everything lesser than 0, strictly lesser than 0, that's why open interval. -infinity to 0, everything is good. Everything will give me positive inside the square root. Or else, if the numbers are greater than or equal to 1, that is closed at 1, that means including 1. Including 1 to infinity, everything will give me a positive input inside the square root. So finally, this is my domain. These are the numbers I can input to get a valid output. And the second notation, which is the synthetical notation, there could be different ways of writing it. D is the set of all x's belonging to R such that x, either you can write down belongs to, or you can write down that it does not belong to. I want to give you that picture as well with this question, so that is why I'm writing it in terms of does not belong to. If x would belong to minus infinity to 0 and or 1 to infinity, then where should it not belong? It should not belong to closed 0 to 1. That's the excluded part from the domain. What numbers are excluded? All the numbers which are in between 0 to 1, including 0, excluding 1. You can visualize it on the number line as well. Number line is a very nice way of figuring out domain. But the only thing is, I just tell my students to be a little careful with number line method whenever you have cases. Please create your broad cases and then move on to the number line. When I say broad cases, for example, in this example, if you are considering positive numbers, do not forget about negative numbers, because a ratio could be positive even when the numbers are negative. So here is your 0. You're saying everything from 0 till this side, negative numbers. And then say here you have 1. Including 1, everything on the right is a part of the domain. So what is not the part of the domain? From 0 to 1. Of course, since inclusion is to that side, so excluding 1, and here since 0 is not included on the other side, so 0 will be included in this side. So this much is deleted from the domain. That's how I've written the set domain with not belong to. Thank you.